Hello, it's Keith here, and this is lesson 1 of the simple series of my PowerPC assembly programming tutorials. We're looking at the GameCube today, and we're drawing bitmaps. Now, the simple series, we create a single SM file that does a single job, and the job today is drawing to the screen. Now, on the GameCube, this is a little bit more tricky than you might expect. The screen is 640 by 480, and there is sort of 2 bytes per pixel. In the terms of memory allocation, there's 2 bytes per pixel. However, the color information uses 2 bytes, and those 2 bytes are shared between 2 horizontally neighboring pixels. So we've got 1 brightness byte for each pixel, but the color information is shared between pairs of pixels, and this creates color distortion. So to sort of show what the source bytes actually produce as colors, we've created a sort of grid of a line of colors here that use various values that we'll see in our code, and we've got 2 versions of the sprite. Now, the first one is a 1-to-1 scale, so this is 1 pixel is 1 pixel. Now, this means that the color attributes are shared between some of the pixels. This one is double-sized horizontally and vertical, and so now each pixel here uses 4 bytes of 2 neighboring horizontal and vertical pixels, and this means that the colors aren't being shared with any of the pixels, so that is properly represented. Now, if I just close this actual emulator window and see this zoomed in version, we can see here, if you look at the hair and the around the face here, the cyan shadow around the hair and the face there, and you look at it here, you'll see that it's turned slightly blue here. It's become a sort of a deep blue there, but here you can see it's just pure cyan, and it's this pure cyan that is the correct version. This version is the incorrect version, and that's because this is 1-to-1 scale, and 2 of those pixels are having to blend the color information between them because we simply don't have enough color information to properly represent what the source information might contain. So as I say, the example is working around that by doubling the size, and the reason I'm doing that is I'm a retro programmer. I work at 256 by 192 most of the time. 320 by 240 is an absolute luxury to me. 640 by 480 is far more than I require, and when that 640 by 480 is coming with disadvantages, in other words this color problem, it certainly isn't something that's going to particularly entice me. Now, how do we actually define the colors then? Well, basically, if we go over to our source code and quickly take a peek here, well, you will see whenever we want to define a color, we are loading R3 with a 32-bit value here. We're doing it in 2 parts because of the way that the PowerPC works with its immediates. So basically, what we're doing here is we're defining the brightness for 2 pixels. This is the first pixel, the leftmost one, I think that is, and this is the rightmost one. But then we've got 2 pieces of color information, which are CB and CR. That's the official documentation names for them, and that's not blue and red. Don't think that's blue and red. It's not. It's 2 color encoded attributes that define the color offset to the black and white brightness. So if we just were working in black and white, we'd have a very easy time. You can see here we're loading black, and the white attribute is 0 in both cases. Then we're loading mid-gray, and it's 80 in both cases. And then we're loading white, and it's FF in both cases. And the 80 is basically the it's basically the midpoint for the color information, which means there is no color. Anything else, we have to start using offsets. So for example, if we are using red, here is the color offsets 5, 4 and FF for the red. Here is the green, 2, 9 and 1, 2 for the green. And here's the blue, FF and 6B for the blue. And you can see here as well the brightness information is sort of all over the place, and that's because the brightness information, it's not just a sort of flat average of the colors or anything. It's more complex than that, and we have a formula that we use to do it. So if we've got the color that we want to use in R, G and B, then what we would first need to do is we would need to take the 2 neighboring pixels that we have to combine, and we would have to basically add those together and divide them by 2 to work out the average red, green and blue components for the 2 pixels that are going to have to share color information. What we then do is we can take the brightness simply by calculating using this formula with the original red, green and blue that we want those pixels to contain, and that will calculate the brightness for each of those 2 pixels. Remember, there are 2 brightness attributes. That is Y1 there, and that is Y2 there. But then we have to calculate the B and R components, and we do that via this formula here. So this is taking the average of the red, green and blue, and it's multiplying them with this formula here, and that calculates the CB and CR components that we actually want to use in our code here. So that's this part here, which is 80, which if you look here is basically the default if all the passed in RGBs were 0. So that's what we do. Now here I've got a list of colors. This is from today's example, and the component information that we need to get those colors, so you can have a look at that. Now you can use these formulas. If you just get a calculator out, you can do it that way. If you use my Sprite editor, which is included in the downloads, if you go to the PowerPC menu and GameCube, we have two options here: save raw bitmap double width. That will create the double width scaled one, which has the half resolution but the full unaltered colors, or the full resolution, the normal resolution one, which is this bottom one below, and that is calculating the pixel information using these formulas. If you just want a quick calculation though, you can also go to my website and you can download this color conversion spreadsheet, which is a LibreOffice document, which you can see here. It's also got this information here just for clarity, but you can basically type in information here and you will get a potential color attribute here and a brightness offset. So you would need to calculate this sort of twice if you wanted two brightness offsets. But this is what I used basically to calculate these test colors in today's example. So if you want to do this and you don't want to mess around with the maths, which I can fully understand, then that is a way you can do it. Okay. Let's go over and let's take a look at today's example. So at the start of our example, we're defining a text block and the start of our code. Now, what we're going to do first is we're going to define the memory address that we're using for VRAM. Now, it's this memory address here, and we load it into one of the hardware registers at this address here, CC00201C. Now, the C part, that top nibble of C there, defines that we're going through the cache. That's the cache through address. So that is the same address as if we just replace that with a 0, in fact. But the cache through addresses we use for the registers. And so, but this address here, basically the top C is sort of irrelevant there. You could consider that to be a 0. It would be the same address because the C there just represents the cache through address, not using the cache. Now, we're going to do a few things here after that. Now, we're going to first look at this sort of main code, and then we're going to look at each of the subroutines and see what it does. So the first thing we're doing is we're clearing the screen using the CLS routine and using this color here in R3. So that is the black color. And then what we're going to do is we're going to use this routine called quick block, which is a very simple routine I use to create that strip of colors here. So all quick block does is it draws one block here, a 48 by 48 block, I think that is, and then it moves across 48 pixels, and so we can just quickly show lots of blocks as a nice test. So we've got the colors here that I calculated all of these with that spreadsheet I showed you earlier, and we're showing those blocks to the screen just so we can see them. And of course, if you want to try out your own colors and play with this yourself, this is how you can do it. Just change the two parts here for the full 32-bit value and run quick block, and you will set a block on the screen with that color. Okay, we're now going to use our drawing routines, and they're both virtually identical. We've got to draw bitmap 1 times, which is the unscale version, the 1 scale version, and then we've got the double scale version. Now, the double scale version needs to use a different bitmap. The source bitmap data has been doubled in width horizontally because that means because the color information that's represented in the file needs to be different. It's not doubled vertically though. We have to do that at the drawing stage, which is why we're using a different drawing routine for the second file, so that is doubling the height vertically. So we are we're calculating the screen destination using getScreenPos. We pass an X and Y coordinate here that we want to draw at, and then we load in the bitmap address into R3, the width and height into R5 and R6, and then we run the respective bitmap drawing routine. And then the final thing we've got is an infinite loop here. So that's pretty straightforward. Now, how do we actually calculate the screen destinations? Well, very straightforward. As I say, we loaded that address before as the VRAM destination in the register at the start of our program. And so all we need to do, that is effectively the top left corner of our screen, and all we need to do is calculate the offset to the pixel we want to draw at. Now, each of our lines is 640 pixels, and each of those pixels uses 2 bytes. Now, remember, there's a shared color byte there, but in mathematical terms, it's 2 bytes. So basically, we take our Y line and we multiply that by 640 times 2. And that's what we need to do to calculate the Y offset. Now, for the X offset, that's very straightforward. We just take our X position and multiply that by 2, and we just add those together to the base, and we've calculated a VRAM destination. Okay, let's take a look at the clear screen routine. Very, very straightforward. All we need to do is calculate the total size of the screen in 32-bit values here. That's what we're doing here. So basically the screen is 480 lines tall. There are 320 32-bit values across the screen, 640 pixels, 2 bytes per pixel. So that's 320 32-bit words there. And then all we're doing is we're moving that total to the counter register, and then we store the value in R3, which should be the color. If it's not, we're going to get a weird effect. And we write that to the screen, filling effectively 2 pixels. We move across the screen by 4 bytes. We've filled 2 pixels, 4 bytes there, so we do that, and then we repeat until we've cleared the screen. So that's the clear screen routine, and now let's take a look at the quick block routine. So this is designed to draw a block to the screen for our testing, and you can see a lot of the code is actually backing up registers so nothing gets changed. So basically all we're doing here is we're using getScreenPos to calculate the VRAM destination of the current block. We then use fillArea to draw the block to the screen, and then we just restore all the registers when we move horizontally across the screen 48 pixels so that we can easily create that color strip that we saw before without any extra code. This was just designed to allow the starting code to be as short as possible. The fill area routine is very straightforward. It's basically a modified version of the sprite drawing routine with the sprite code taken out. It's just you filling with the same value and over again. So we've got R4 here, and that's our VRAM destination. We're moving that into R8 for this line, and then basically all we're going to do is we're going to take the X count and move that into the count register here. And then what we do is we store the color we want to fill into the VRAM destination, add 8 to the VRAM destination. We're storing a word, so that's a 32-bit value. That's 2 pixels, 4 bytes. So we are adding 4 because we've written 4 bytes. We repeat until we've done a line. And then what we're doing is we are taking that original VRAM destination and we're moving down one line. So we're drawing across, moving down, drawing across, moving down like that. And so to move down a line, we just 640 pixels, 2 bytes per pixel. So we just add 1 to 80. That's all we do to move down a line. We decrease our Y count and we repeat until we've drawn the block. And then of course that would then return to the calling routine. Okay, and of course you can see we're just running that over and over again. So that's all there is there. The final thing to discuss is the drawing routines. Well, let's take a look at draw bitmap 1 times first. As I say, this is quite similar to what you just saw. All that's different is we are loading in different byte data each time we draw to the screen. So we are again taking our X width and loading that into the count register. We're taking the Y destination, we're backing it up into R8 here, and then what we're doing is we're loading a 32-bit value here, which is effectively 2 pixels, 2 screen pixels that is, and we are loading that into R0, and then we're storing it to the screen in R8. Once we've done a pair of pixels here, we are moving across the screen, and we're moving across, incrementing the source data as well. We're repeating until we've done a line. Like before, once we've done a line, we add 1 to 80 because that's the width of a line in bytes, and we just repeat until we've done the entire line. So that's the 1 times version. Now there is the 2 times version, which again is just a modified version of that. Now, as I say, our source bitmap is stretched horizontally, but it's not stretched vertically, so we need to double it up vertically. That's the only difference. So again, we're doing that thing with our X position, moving to the count register, backing up our VRAM destination. We are loading a 32-bit value. That's 2 pixels, but remember they are effectively doubled in width. So this is 2 pixels that will both be the same color in this case, because the source bitmap is horizontally doubled in scale. So we are loading that in, storing it to the screen, but then we're storing it a second time to the screen, 1 to 80 down, and that's because, as I say, it's not doubled vertically in the source file. We're doing that manually ourselves right here. We then add 4 to our source and destination, moving us across the screen and across our source bitmap data. We then repeat until we've done the line. Now, once we've done an entire line, we need to move down before we were adding 1 to 80. But we've already done a second line here, so this time we're doing 1 to 80 times 2, effectively moving us down 2 lines. We then just repeat until we've done our bitmap, and that draws the bitmap to the screen. So there we go. Drawing the bitmaps to the screen is very straightforward, really. I mean, there's nothing particularly shocking about it. The only annoying thing is this color thing. I'm no expert in sort of analog TVs and things. I do know that NTSC color representation tends to blur neighboring pixels in this way anyway. So it might be that a lot of this choice was made because they knew that the colors couldn't accurately be represented anyway on the old analog TVs. It could be that. This kind of color encoding is very, very common in things like video compression, and it makes a lot of sense in that case. It just doesn't make a lot of sense to me where you've got 2 bytes per pixel and you are compressing in this strange and frustrating way. Systems like the PlayStation used 15 bits per pixel. They had fantastic color. They didn't do this. This seems overly frustrating for the programmer, but anyway, it's what it is. That's what we have to use. So there's how you can do it. And as I say, go to the website. You can download today's source code, the build script. You can download my Sprite editor. It's free and it's open source. So you can get the source code on the website as well, and you're welcome to modify it any way you want. And as I say, you can also get that spreadsheet, which will help you do the maths if that's the way you want to do it. But of course, the way I did it was I copied those formulas straight into Sprite editor, and I'm sure you can do the same thing yourself if you want to create your own programs to do your own conversions and things. Anyway, hope you've enjoyed what you've seen today. Thanks for watching. Like and subscribe. We've got another video coming on how to use the joystick. We're going to move the sprites next time. Goodbye now.